All right, good morning, everyone. We'll do a slow start here while people trickle in for the meeting today, but thanks for joining. All right, let's go ahead and get started. Yeah, thanks again for joining. I'm filling in for Julia today. She had a last minute conflict that pulled her away, so you're stuck with me today as MC, but we've got a really good lineup. So thanks for being here for the next installment of the i2X First initiative, put on by CETO and WETO offices at the DOE. So just a couple of reminders as we get started. The first half of the meeting is recorded and it'll be posted on the ESIG website. So that'll be the presentations and things like that. So if you don't want your voice to be recorded, just please keep your phone on mute. And then same thing with cameras. And then the second half of the meeting, we stop the recording after the presentations for open discussion. That part of the meeting is not recorded, so we encourage everyone to chime in and participate as much as possible. Just a couple of quick key goals and outcomes for the i2X First initiative. Really the goal here is we're trying to facilitate an understanding and adoption of the new and recently updated standards, particularly related to existing and newly interconnecting wind, solar, and battery plants, so inverter-based resources. The forum is intended to convene industry stakeholders for a practical and more harmonized implementation of these new standards. And like I mentioned, we record the presentation portion of the meeting, and then those presentation slides and the recording will be made available on the ESIG website. So we'll drop in the chat here where those locations are. And additionally, we have a summary document that we, after each meeting, we add to. It's a really good reference that really is just intended to capture the discussion and the recommended practices and some of the challenges and the gaps. Really just trying to lay out all of the really great technical discussion that these sessions have been having. So just in terms of the leadership team, we've got Cindy Bothwell from the WETO office. We've got Robert Reedy from the CETO office, Will Gorman with Lawrence Berkeley National Lab, Jens Boemer, who's a presenter here today from EPRI. As I mentioned, Julia convenes and coordinates the initiative from ESIG, and then myself, Ryan Quinn from Elevate Energy Consulting, helps support Julia in that effort. So just real quick, going through the last meeting on what we talked about back in June. So we had 3 presentations. The first one was from NERC. We received a really good progress update on the milestone 3 projects under the FERC 901 umbrella of standards revisions that are going on. Those are the standards relating to model validation, system model validation, the uniform modeling framework approach, etc. Talk a little bit more about that. And then we had Vestas present on their perspectives related to the current state of IBR modeling in North America. And then Electronic shared some practical perspectives regarding approaches and recommendations for modeling legacy IBR plants when maybe data is not readily available, like for new plants. We also had some structured discussion and some Q&A. And again, all of that material, the recordings, presentations, etc., are all posted on the ESIG website. So in terms of what we heard last meeting, like I mentioned, the milestone 3 standards development is underway. Those standards are addressing data sharing, model verification, use of particular models in certain studies, and then system model validation, including and all of those activities, including IBRs. The 3 standards projects all had initial ballots not too long ago. All of those ballots failed. And that's not uncommon for initial ballots at the NERC standards level. But it does, we've got this looming November deadline that FERC has mandated. And so there's a lot of focus on, okay, the next ballot and the ballot, any subsequent ballots after that, to make sure we collectively as an industry meet that deadline. So it just kind of highlighted this potential tension of the compliance needs and the standards development work with the feasibility of the implementation of those standards. There's also good discussion about the upcoming milestone 4 work, which is the final phase of the 901 activities. Milestone 4 is really sort of next year's tranche of work with a deadline of November 2026, but the drafting teams and the efforts are now starting up in preparation for the heavy lift next year. The milestone 4 work is related to IBR specific considerations in operational planning and long-term planning assessments. So these are the TOP, IRO, PRC, some of the PRCs, and the TPL standards. Like I mentioned, we heard electronic shared thoughts on legacy modeling, and particularly the importance of accurate EMT models. And so again, modeling legacy plants can be challenging, particularly in the EMT realm when you don't have access to good information, readily available information. And so without high fidelity models available, you run into the risk of needing to make assumptions on those facilities. And those assumptions can lead to inaccuracies in the models, which subsequently can lead to inaccuracies in the studies and can lead to potentially misleading decisions being made. And so they just need to have care and caution when going through that exercise. In some cases, it's a necessity. You may have an OEM that's gone entirely out of business, or some other challenge of getting any information or sufficient information for the facility. And so really, I think we hear this from technical experts across the field, where upfront modeling requirements and getting good, accurate, OEM-specific, validated models early, and then making sure we maintain those models through the life cycle of the project, and we address change management issues. And when the site goes through modifications, we continue to get those good models. The OEMs in particular are very engaged when the sites are coming online, pre-commissioning, commissioning, etc. And so it's a great time to get good, high quality models. But we also have this big tranche of legacy assets out there that we need to make sure that we can represent and model accordingly for these studies when needed. Lots of discussion at the last meeting around user-defined models and standard library models, the pros, the cons associated with each. And in general, the standard library models are easier to understand, they're easier to use, they're fully transparent, they're simplified diagrams, and in some cases they can represent at least the general behavior of IBRs. They're mandated to be used in the interconnection-wide models, etc., through the FERC 901 process. But having OEM validated, accurate, site-specific, user-defined models where you have much more of the detailed controls represented, whether in positive sequence simulations or in EMT, is generally preferred and recommended, particularly for interconnection studies or local reliability studies, etc. And so generally those will yield better outcomes, although they are in some cases more difficult to understand or use, and often will require OEM engagement, OEM validation, and support documentation to be able to use those models. So really, again, a balance and a trade-off, some uses for some models and some uses for other models. So just really understanding the specific type of model, the scope of the study being done is really a necessary thing. We also talked about commissioning and the potential gaps associated with commissioning, particularly related to models. That's been a systemic discussion and observation through the NERC reports and a number of the guidelines, etc. And really just making sure that the IBR plant that gets commissioned, and commissioning is really a crunch time where it's all hands on deck. We're trying to get that asset, online, tested, and up to commercial operation. And so often in the past, I think collectively as an industry, we've heard these observations many times that the models tend to fall by the wayside in terms of making sure that what got studied during the interconnection process and represented in that model is actually what gets installed in the field. And if there are any discrepancies or differences, that gets reevaluated after the interconnection process, after the commissioning process, to make sure we get trued up models, right? And so the whole goal, and Jens will talk about this, of IEEE 2800.2 is really along the commissioning steps is to produce data. The commissioning tests generate lots of data that can be used to validate the models, particularly for the small signal disturbances. So the bump test, the voltage reference step test, frequency reference step test, etc., ramp tests, things like that. They miss, they don't, commissioning tests don't do large disturbances. We're not applying faults every time we do commissioning. And so that's really where the post-commissioning performance monitoring and model validation work kicks in, which is also a core component of .2. And then last thing that really was a highlight of the discussion section of the last meeting was really just being clear and understanding that when we're looking at modeling requirements, we've got, model quality tests, and then we've got studies, and there's a difference between those, right? So we will often have a single machine infinite bus type model quality tests. So these are not only can check the quality of the models, but they can also make sure that the plant, as modeled, meets a set of interconnection requirements or performance requirements. So, you can think of the performance conformity testing of the plant to make sure that, it's meeting a certain response time, ride-through performance, etc. And so those tests are often implemented by transmission planners and planning coordinators to make sure they're getting good models as a prerequisite to entering the queue, for example, or into the cluster study. That is a notably different thing than when you put that model into the system base case, and then you run contingencies on the system and you're looking for system impacts, right? And so you may find that a plant behaves properly for the the performance tests, but that it runs into instability issues or there's system performance issues when you put that actual plant on the system. That's to be expected because the system is operating with different system operating limits and limitations and other plants where you might run into controller interactions and things like that. And so both are really needed and are different parts of the interconnection process. And you see that again in the .2 work as well. So those are kind of the key themes from the last meeting. Today we're going to focus on the concept of IBR Plant Design Evaluation, which is really a core central aspect of IEEE 2800.2. There's all various types of steps, but one of the biggest ones right in the middle there is the IBR Plant Design Evaluation. So this is session 1, and then next month in August, we're going to have session 2 because it's so meaty. So stay tuned. We have a really good lineup of presenters. And we've got meetings throughout the rest of the year and into, up through March of next year, where we're going to have a hybrid workshop at the ESIG Spring Workshop. So again, you can sign in. I think Brooke dropped them in the chat. You can sign up for these meetings if you don't have them on your calendar already. And again, all the material is posted there. If you just go to the ESIG website or type in ESIG i2X first, it should take you to that website. So we've got a really good lineup today. We're going to have Jens Boemer from EPRI is going to talk about IEEE 2800.2 IBR Plant Design Evaluation overview, kind of what's entailed in the set of recommended practices. Rishi Maharaj from Engie is going to talk about developers' perspective associated with IBR Plant Design Evaluation, and then Patrick Hart from Mortenson is going to talk about EPC, engineering, procurement, and construction perspective with the design evaluation steps. And then we'll go into discussion. We facilitate discussion on the using Slido. So if you go to slido.com, I believe the code for this meeting is hashtag first3. I think that will be dropped in the chat as well. We take all questions through Slido. So if you have any questions, please feel free to use the Q&A. It's open throughout all the presentations. And we use that to facilitate what questions we're going to take at the end of the presentation. So all 3 presenters will present, and at the end, we'll open it up for a Q&A. Rather than duplicate questions, if you see any questions that you really like, feel free to upvote those questions. We essentially take the top ones, the top voted questions are the ones we start with, and we start working our way down. And then we've got a couple questions. So just to kind of spark early thoughts as we're listening to the presentations. How is IBR Plant Design Evaluation carried out today? If you think about, regardless if you're on the transmission side, generation side, third-party support, how is that done today? How is that compared to, say, for example, what we're going to hear from Jens and the other gentleman? And then, is it sufficient? Do we have any gaps? Are there any issues with the practices that we have today? And then how can we improve design evaluation to ensure future reliabilities? So we mentioned, for example, from the last meeting, the challenge with getting accurate models during commissioning. So that's one step of the process, and the IBR plant design evaluation happens a little before that, but is interrelated with that step. But we can sort of think about, as we're going through that interconnection process and we're evaluating these IBR plants, are we doing enough today? And if not, how do we improve? So again, feel free to use Slido, use the Q&A, feel free to drop your questions in there. And I think with that, we'll jump right in. And last thing real quick, just DOE's code of conduct for virtual meetings. Assume good faith, respect differences of opinions or perspectives, listen actively and respectfully, build upon others' ideas, try to learn and engage, and encourage others to speak up and foster a collaborative environment here. So with that, we'll jump into the stakeholder presentations, and I will turn it over to Jens.
Hey everyone, good morning or good afternoon. Thank you, Ryan, for that introduction. Thanks to Julia for inviting me. I'm Jens Boemer. I'm a technical executive here with EPRI. Many other people contributed to this presentation. And I had to arbitrage preparing this presentation between preparing my daughter's birthday, which is today. So congratulations to Elle. Any mistakes you can attribute to me focusing on preparing her birthday. With that, let's actually look at some of the content here. So one way to look at this is, in the past, when it comes to increasing amounts of large inverter-based resources and how much they represent the generation in the grid, and how much we actually looked at scrutinizing their reliable operation, that there were very little or insufficient performance specifications in the past. Fortunately, we are beyond that. Many of the transmission entities are adopting more specific requirements, and we also have standards like, for example, IEEE 2800, but there are also other standards available around the world. Utilities are specifying their own performance requirements based on their specific needs. But that does not bring us all the way. What we really also need is to look at verification of these requirements. Now, some people could say, well, conformity assessment could simply be done by checking a box whether an inverter or other equipment has been certified, and then have a little checklist for the plant. And maybe that takes us a bit farther than where we used to be in the past to actually verify that at least, say, the inverters could ride through voltage dips or can provide a certain reactive power to the IBR plant. But really, the gold standard is to look at the whole plant in detail using validated equipment models and model and characterize the full plant's response. And that's really what IEEE 2800.2 is aiming for. Now, IEEE 2800 provides performance requirements and capability specifications. 2800.2 provides this plant level perspective. At this point, just to remind everyone, there are no plans for IBR equipment certification along IEEE 2800 requirements. So we're kind of skipping this middle step here that some people might have looked for. So we're not planning to do that at this point. And 2800.2 is currently in balloting. So let's keep our fingers crossed that it makes it through balloting. As a matter of fact, it received a 84% approval rate and met the quorum above 75% of balloters participating. There are about 280 or so balloters, I believe. So it's a pretty significant document. It's not the only document. It's certainly not the best document. And it's not really a new document, because what it tries to do is it tries to summarize practices that we believe are already being used in many areas around the world, and to a large extent, or an increasing extent, also in North America. So my presentation is really focused on this last step here, the conformity assessment by unit characterization and plant modeling. And let's just remember, any specifications of requirements without verification of those requirements are really useless. Here's another kind of introduction slide, because we use a lot of different terms when we talk about these things. We are looking at conformity at the plant level. That's what I'm going to focus my presentation on. You could say there's this other dimension to it, which is compatibility of equipment with a certain standard. That does not mean certification, or that the equipment itself meets all the requirements of the standard. But what it does mean is that the equipment can be compatible with the intent of the standard, and can be used in order to support the conformity of the IBR plant. What's also outside of my presentation is any compliance. So all these IEEE standards are voluntary standards until a authority that governs those interconnection requirements actually adopts that. And whether that's a regulatory authority or a individual transmission entity, that depends on the context. And there are a few references here at the bottom of this slide that I encourage you to read to understand a little bit more about the term conformity, which is not as commonly used in the past here in North America, at least. Here's a kind of old slide I used maybe 2-3 years ago or so. I wanted to give like one example for a non-conformity, for example, with IEEE 2800. This was a plant controller interaction that was identified by NERC. And then we tried to map that to the various requirements from the base standard, IEEE 2800, and at least qualitatively assessed which of those requirements were actually achieved and which ones not. And even though in this case the plant did ride through successfully, that's why it says a pass on the voltage ride through, we could tell that from the restoration of output of power after the ride through, the plant did not or would not have conformed with IEEE 2800. So that's where it failed. And even during the fault, instead of providing short circuit current, whether balanced or unbalanced, depends on the type of the fault, this plant went into momentary cessation at a level of retained voltage that was much higher than the permitted 10% per IEEE 2800. So big question now still is, okay, when you have a plant, how can you actually assess conformity of that plant? So this is where modeling comes into the game. And some of you may remember this overview chart that I presented 2 months ago in this forum. What we've been doing here is we've been trying to keep track of which utilities are adopting what parts of IEEE 2800. And what we can see is that clause 10, which is modeling, and clause 12, which is test and verification, yes, they are about to be adopted, but we also see a lot of, I would say, own requirements, not necessarily like references to those clauses at this time. And again, that is not surprising because really the meat that fills and supports these clauses is currently being developed in IEEE 2800.2. So the point here is at this time, we still see a fairly heterogenic set of requirements for performance test and verification and modeling. But we expect that could possibly change going forward as IEEE 2800.2 becomes available and entities might also further align with them. Now, one entity, and I apologize for calling anyone out specifically, but since all of this is publicly available already since last week, I am calling out MISO and would like to draw everyone's attention to paying attention to what MISO is proposing with regard to IBR modeling requirements, because they also do that to support conformity assessment. And you can go into the details here, which we don't have time for, but the takeaways from the presentation, they are literally presenting right now, I guess, in this hour or maybe next, in an hour from now, under the link provided, is that while both TSET, user-defined, and EMT models are required at application for IBR plans, the PSSE user-defined model is not required until the execution of the generator interconnection agreement, or at least that is what MISO is proposing. This is all still a draft, obviously. And also the interconnection customer is responsible or should then be responsible for producing a so-called dynamic model quality and performance test report. And then it is up to the TO or the MISO to review that. So you can find more information at the provided link. Stakeholders all publicly available. And they are looking for feedback by August 5th. So looking at this whole daisy chain of conformity related to IEEE 2800.2, you have probably seen this chart many times, so I'll keep it simple and say we are focusing here today further on the IBR plant model development and the IBR plant design evaluation. Those both go hand in hand. And if I hadn't mentioned it before, not only was the initial ballot of .2 successful, we're also now working through more than 700 comments before we recirculate the document. But it's looking good so far. Just a reminder, requirements of 2800 apply mostly at the point of measurement. There's only a small set of requirements, specifically the ones related to current injection during abnormal voltage requirements that apply at the inverter level or the point of connection. Now here's an overview of the initial ballot draft of 2800.2, and we'll zoom a little bit into the clause 7 here. Clause 7 covers review of capabilities to some extent. I would say probably not sufficiently at this time, but maybe sufficient enough for the first edition of this document. Review of settings, settings of IBR unit controllers, supplemental IBR device controllers, power plant controllers, and so on. Also, protection is covered, like protection within the plant is covered in that section. And then the review of equipment model validation report, which is, checking documents and actually looking at this report. For example, at that report that MISO proposes interconnection customers shall produce. But then there's this big section on modeling and simulations that includes model quality checks, and there's an annex that elaborates a bit more in detail what quality checks actually could be, both at equipment level as well as for the IBR plant level. And then section 7.3 provides plant model development and verification. Sorry, section 7.2 is plant level development and verification, and then 7.3 are the performance tests. And that's what we're looking at a bit more in detail here. So we're not saying that this is the one and only solution. This is just like one solution, how to go about these things. The intent of these performance tests is to assess performance of a given plant connecting to a specific grid connection point that has certain characteristics, for example, in terms of weak or stronger grid, SCR ratio, and X to R ratio, to run some tests that assess whether the plant is in conformance with the IEEE 2800 standard or not. Now let's remember, and I think, Ryan, you mentioned it earlier in the introduction, this does not sufficiently verify that the plant will in all conditions operate reliably, and whether the power system as a whole will operate reliably when these tests are successfully passed. That's not what this is about. This is about conformity. There may be a later step that is about impact assessment and stability of the whole grid. But focusing on conformity of assessment of that given plant, 2800.2 proposes specific tests for reactive power capability, reactive power response, and voltage response, frequency response, low voltage ride-through, high voltage ride-through, or even transient over voltage, and positive sequence voltage phase angle change ride-through. So the standard actually says that these tests shall be run at a strong and also at a weak grid condition. But not always does the transmission system planner provide specific numbers for what that actually means. And IEEE 2800 in clause 4.1.1 recommends that the transmission entity provides numbers, but if they don't provide these numbers or conditions, then 2800.2 suggests to run these tests once at a strong grid with SCR 20, and then at a weaker grid condition with SCR 2.5. Now, these are arbitrary numbers, and therefore you can adjust those numbers when you engage in conversations with the transmission entity. Also, to point out is that these tests shall be run for various levels of active power prior to the disturbance. Usually that will be the maximum power output or the interconnection continuous rating, and then also the minimum rating. For example, for a wind plant, that might be around 15 or 20%. But in those cases where the IBR plant has storage, then these tests shall also be run at the maximum active power absorption of that storage element from the grid, and that's called ICAR, interconnection continuous absorption rating, as well as around a zero operating point. Because the idea is to really test whether all the controls and the sign conventions and everything has been implemented adequately. So let's actually look at some of those tests. We're using a infinite bus with a controllable voltage source and a adjustable equivalent grid impedance to generate the test signals. The grid can represent 2.5, 5, or 20 SCR. We, in this case, set up a aggregated model for a plant with 211 MVA total capacity rating that can operate at 200 MW active power output of ICR, and all the plant measurements are at the POM. This has been parameterized for stable operation in medium strong grids. And we are running both a PSCAD and a PSSE model using certain available generic models, which we can then configure in different ways. And the IBR units have their local voltage control disabled. Also, their fast frequency response is disabled. So they are following the power plant's controllers P and Q set points. And it's really the power plant controller that provides the voltage response signals as well as the frequency response signals. So let's look at this. There are plenitude of tests, even more than the ones that we have selected here. We're just going to show you 2 test results for reactive, one for reactive power control and one for frequency ride-through, given that time is really short. Actually, I only have 2 or 3 minutes left here. So let's look at this. We're using the test signals from IEEE 2800.2. This is the strong grid. It has a fairly aggressive control, and we see that both models are more like the PDT model and the PSCAD model are in fairly good match with each other, and they both adjust their reactive power within about a second of the RPR voltage step change. Now, when we go to a weaker grid condition of 2.5, what we see is that the plant response is much faster with those same control parameters. So the question comes up, okay, is this kind of high voltage after, when the voltage changes, is that still acceptable from a conformity viewpoint? Now, when we change the control and make it less aggressive, we actually see that we have a less high voltage. So maybe this is better. Now the reactive power responds within 6 seconds. So the plant's controls have been intentionally slowed down. So those are questions that you can ask yourself. We're not going to give you the answers here. We have a kind of EPRI forum where we're going to look into that in detail. But those are approaches and questions you can ask yourself. And then for the frequency ride-through, we've run a similar test. Now we're using the test signal from 2800.2, and it goes all the way to the edges of the ride-through zone. And that is like a 5 hertz per second rate of change of frequency all the way down to 0.95% of 60 hertz. That's a very strong, very significant frequency step. Now, question is, how realistic is that? Would that ever happen in the grid? But that's not the point here. The point is, let's try to test the model, whether it conforms with the standard. And to make it more fun here, 2 more slides. We don't have time for it in detail, but question is, when does it actually make sense to do any of these verifications? And we would say it makes sense as soon as you have validated IBR equipment models and verified IBR plant models, which then also build on the validated IBR equipment models. And you have that early on in the process because you tell your OEM and your plant developer, you have to strictly follow all the IEEE 2800 rules. Maybe they use generic models to define the reference responses, and then they guarantee that every time throughout the engineering process, that they verify that their design actually meets these responses. Then at the end, after the plant has been constructed and also evaluated in the field and verified for the control settings, then you would still need to assess one more time whether the verified plant model actually meets these requirements. And last not least, if you're interested in learning more, we have a forthcoming IBR identification and conformity assessment tool that we will make available to our EPRI members only, participating in some of our research. That is the tool that can automatically run these tests and also will be able to visualize conformity areas. And then we are launching a collaborative forum that supplements and complements these i2X scores for EPRI members to go a bit more into some of the depths. And if you're interested in that, you can look at our website. And with that, thank you so much. And I'll be happy to answer questions in the Slido.
Awesome. Thank you, Jens, very much. Great presentation, very informative. Definitely hit on the, all of the key topics, the challenges, and the kind of the core focuses of the design evaluation. I generally think the when in the process is this most appropriate is something that will probably come up in the Q&A, I'm sure. I think it's a hot topic. Great. Well, next we're going to go to Rishi with Engie to hear about developer perspectives. Rishi, I'll turn it over to you. Go ahead and share your screen.
Thanks, Ryan.
Perfect. It's great.
All right. Well, that was a tough act to follow there from Jens, but I'll do my best. I'm gonna start my timer so I don't take up too much of your time, since this is such an exciting topic. So good morning or good afternoon, everyone. I want to maybe just start by giving a brief overview about the company that I work for, Engie, and exactly what our business are. So we're a renewables developer and owner. We have today about 11 gigawatts of renewable, both wind, solar, and storage operation across North America. And we work on projects both in the development phase and as an owner operator. So this is one of our corporate PR slides, just to give you a very basic idea about what the footprint and what the business is. What do I do in this very large company? I work in the operations engineering department, which means that we work primarily, on assets that are past COD. And we have, I think, an interesting perspective on conformity assessment and compliance, because we are looking at it in a backwards looking way, because we are introduced to all of these things when operational problems with IBR plants occur in the field. So generally, me and my team are not working on studies that are happening during the design phase or during the interconnection phase of plants. However, whenever an IBR facility that we own or operate has an actual operational performance issue or apparent failure to perform or apparent failure to meet interconnection requirements, we are the people who are going to start digging into why that happened. And that's where we gain an interesting perspective maybe on what studies have or haven't been done during the design or commissioning phase of the project. So what I'd like to address today is really just a handful of points. I want to go a little bit into what is typically the contractual structure around the development, design, and commissioning of an IBR plant, at least from our perspective at Engie. It may be different in other companies. I think that's an important element that needs to mesh with design evaluation and with conformity assessment, because standards like IEEE 2800 really address the issue from a technical point of view, which is logical for an industry standard. But all of that really needs to ultimately map to the contractual and project management structure in order to happen during actual project, and that's where a lot of challenges arise. I'm going to talk a bit about what I see as kind of the status quo situation of conformity assessment or design evaluation as it is today prior to IEEE 2800. So as Jens presented very well, there is adoption of elements of IEEE 2800 that is happening across different regions in North America, but that is still at a relatively early phase, and the vast majority of projects that we've worked on up to this point have been outside of the context of 2800. And so when we're talking about design evaluation, we're talking about evaluation with respect to requirements other than IEEE 2800, those requirements that were kind of to the left of the desired future state in Jens's slide about how the industry is moving forward. And so there's a bit, probably an overlap between conformity and compliance, because today or in the past, we haven't had comprehensive voluntary standards like 2800. And we've been primarily dealing with interconnection requirements in the context of mandatory compliance with mandatory requirements. I'll touch briefly on what I see as maybe some of the opportunities for conformity assessment from the developer perspective as we continue to move forward with implementation of 2800 by AGIRs, as well as the anticipated future P2800.2. And finally, just some general recommendations about what I think we can improve in our processes. So I think typically when we talk about IBR plant design, we think about two buckets of entities. One is the developer or owner, and the other are everyone who's on the other side of the POI, which may be transmission owners, transmission operators, planners, RTOs, ISOs, et cetera. And one thing that I want to spend a bit of time on is to present that, yes, that is true. However, there are a lot of pieces within the developer side, because typically a developer is not a massive engineering company that is actually directly performing all of the activities that are needed in order to develop, design, build, and ultimately operate an IBR plant. In our company, almost all of the engineering work that will be done is going to be done by some type of third party that we contract. That might be an OEM. If we're building a wind facility, typically we are going to purchase the wind turbine and wind plant controller equipment directly from an OEM. There will be a variety of engineering consultants. There will be an EPC contractor, and the EPC contractor may have one or multiple levels of subcontractors doing engineering activities below that. And so when we talk about something needing to happen on behalf of a developer, who might actually be doing it could be quite different depending on what the activity is and when it needs to happen. So if you now think about trying to comply with any type of requirement, whether that is a mandatory requirement that is legally enforceable like a NERC standard, whether it's an ISO rule, or whether it is a voluntary requirement or consensus standard like 2800, the point I would like to make is that there's a lot of coordination and communication between multiple parties who are working on different elements of the project that's required in order to actually bring that to fruition in the real project. And that's really the area where, from my perspective, I see a lot of the existing pain points, gaps, and maybe failures to get to where we want to be. They occur in the gaps of those various scopes of work. As a developer, I think if you want to achieve something in your project, one of the biggest tools that you have to do that is to go to whoever is the party who's going to actually do that thing and write it into their contract. If you would like to have an IBR unit that meets a particular technical requirement, we are not developing IBR units. OEMs are doing that. So we need to take that and translate it into an OEM requirement that is contractually binding upon the OEM. And what I'll get into later is really maybe what are the limitations of trying to achieve conformity or compliance, whatever the case may be, primarily through writing things into a contract. This is an extremely simplified kind of typical project hierarchy as it would be for Engie. So at the top, you have the developer or owner. We are contracting an engineering, procurement, and construction contractor to deliver the bulk of the plant. They themselves are likely not doing the engineering work. They would typically subcontract an engineer of record. That's the engineering consultant who will be doing most of this, the plant design, the substation electrical design, civil design, et cetera. The EPC, in many cases, in Engie, it's the case for solar projects that the EPC is also purchasing the IBR units. So the IBR unit OEM is a subcontractor of the EPC. they are procuring the plant controller, but they're likely not developing it themselves. So there's a plant controller OEM who's also under the EPC. They may be hiring one or more specialist engineering consultants other than the engineer of record to do things that the engineer of record may not have the expertise to do. And they may be also, and they will also be hiring commissioning contractors who, again, are likely not employees of the EPC themselves. They're subcontractors. Then on the owner side, we have some things that are outside of the EPC scope. As an example, in Engie, we typically purchase some of the major substation equipment, like the main power transformer and high voltage circuit breakers, outside of the EPC scope. So we have other equipment OEMs. If it's a wind project, the wind OEM may be working directly for us as the owner. We have other engineering consultants, particularly consultants that are doing power system studies and modeling that are not working for the EPC. They're working for us using input data from the EPC. And of course, once we get to the operational phase, the O&M personnel who work for us. And really what I'm trying to illustrate with this is that there are a lot of moving pieces, and I think everyone can appreciate how there's a need for all of these parties to work together. I mean, if we try to map out what are all the interactions just between the boxes that are on this slide, and draw lines between all of them wherever they need to interact, this slide would look like a giant spider web. And yet, each one of these entities is, in actual practice in the project, typically only communicating one level up. So what I mean by that is if the IBR unit OEM is subcontracted by the EPC, it may mean that other parties in the project, like the engineer of record, don't have a direct line of communication to the IBR unit OEM. They have to go through project management at their kind of mutual common point of the EPC in order to get information from each other. If a modeling consultant who's working for the owner needs to get information from the plant controller OEM who's working for the EPC, they may need to go through multiple levels of project management in both owner and EPC in order to get that information. And so interactions between all of these project parties are, I would say, limited, and they're limited to the interactions that are maybe explicitly prescribed in contracts. There's not a lot of proactive collaboration. And just to make everything a little bit more complex, this is the simplest imaginable version of this. If you have, for example, a hybrid project, which might be solar plus storage, this whole structure could be duplicated a second time. You could have a second EPC contractor who's building the BESS portion of the project. You could have a second IBR unit OEM, a second plant controller OEM, and so on and so forth. And so the level of project management complexity doubles, even though both projects are actually directly electrically coupled to each other. So as a kind of a thought experiment, I want to just ask, like, if that is the structure of a project and you're now trying to comply with some new requirement, whatever it might be, 2800 or something else, what does the developer actually now need to do? Because keep in mind, the developer isn't the one actually doing the activities that are going to build up to conformity or compliance. Well, you would have to take that requirement, have to precisely map out what every party needs to actually do, negotiate with all those parties to make sure that they actually have that in their contract and that they actually have the right timing for the delivery of that element in their contract. You then have to monitor and manage whether they're actually doing it. And if they're procuring it from a subcontractor, you may have to check that as well. And then finally, once everyone has actually done whatever they need to do in order to achieve conformity, you now have to do some form of assessment of that, which could be a design evaluation type study. Well, who's going to do that? That's probably going to be another consultant because, as I've said, developers typically do not have a very large power system studies department within their company. And then finally, after you've done all of that, you need to still verify the performance of the actual plant with commissioning tests once you've actually built it. So that's quite a lot. And the question I would like to ask maybe to the industry is, how achievable is that really? If you're talking about a non-expert developer that, as they said, may not even have a power system studies expertise within their company, there's just a lot of places for that to go wrong and not actually have the intended outcome. So trying to do something that is, let's say, relatively simple from a technical point of view can blow up into something that is a fairly complex project management exercise when you consider this type of contractual structure. So finally, you know, the thing that we're all trying to do as developers, I think, is we want to have limited permanent engineering staff. And that's one of the main motivations for subcontracting a lot of these things to consultants. We don't feel that we can commercially sustain having all of those staff ourselves. At the same time, though, that, you know, thinking back to the structure I presented on the previous slide, the developer is the only one that has the visibility of the entire project to actually confirm that something has been done. So how can you deliver that level of technical coordination across the entire project if you don't have that expertise within your company? I'll move on to, you know, talking about a few maybe just examples of pain points or gaps that I've seen come up in conformity assessment today, not referencing 2800, but with existing requirements. So P2800.2 has the definition of conformity assessment is simply that specified requirements are fulfilled. So the first challenge, I think, is what are the requirements? Because as Jens presented, there's, you know, prior in the pre-2800 world, and I think as well after 2800, because 2800 will not form the entirety of interconnection requirements for any particular AGIR. There's a challenge in simply identifying what are actually all of the applicable interconnection requirements. You know, they can be things that come from NERC standards, that come from an ISO, things that are particular to a certain generator interconnection agreement with a TO or ISO. It's not that simple of a question to ask. What are all of the applicable requirements for a particular IBR project? And, you know, keep in mind what I just said, that the developer needs to successfully enumerate all these requirements and translate them into everyone's contract. So they have to actually know what they are. If you don't know what the requirements are, you almost certainly are not going to be compliant or conformant with them. So there's a common pitfall that I see is writing, you know, comply with all the requirements. Well, if no one knows what the requirements are, it's very unlikely that they're actually going to be able to deliver and validate their conformity with those requirements. And many interconnection requirements really apply to the plant level. So it doesn't make logical sense to write a requirement that is a plant level requirement into the contract of a particular entity that is only supplying one part of the plant. So, you know, this approach that I see pretty often of just saying, you know, comply with everything, that really doesn't deliver any results in practice, in my opinion. So I think today, if we look at the status quo of design evaluation or conformity assessment, we're really not doing it comprehensively and proactively. What we're doing is we're doing studies that are mandated by AGIRs that are part of this kind of mandatory path that leads you to commercial operation. So these may be, you know, I put some examples here of particular studies that are required in some regions. These are things that you have to submit and that have to be approved before you can commission your plant. But those studies only address a relatively small subset of all interconnection requirements. So the rest of the requirements that are not addressed by mandatory studies, those are kind of still in the dark and not really being directly proactively assessed by developers in my experience. And, you know, I think that the main takeaway from that is what is verified is done. Everything that is maybe in fact a requirement, but is not actually verified, it is seen as being optional and may not actually be done in practice. And the result of that, of course, is that you will have plants that in actual fact have an inadvertent nonconformities. So this is, I think, you know, maybe the overall takeaway of the last few slides is what is conformity assessment? It's something that everyone thinks someone else is doing. There's a lot of opportunities within this kind of project structure for someone to assume that someone else is actually the one that's doing it because it's not part of their scope of work. And if everyone thinks someone else is doing it, then maybe no one is doing it. So I'll speed up a little bit here because I'm getting towards the end of my time. And one thing I want to highlight is that design evaluation is a study. The output of design evaluation is going to be a study report. But what our ultimate objective is to build a plant that complies with the requirements. And that only occurs when the results of design evaluation are actually translated into the field and verified. And today, I think there are a lot of gaps in terms of verification and commissioning of what has come out of studies. Most AGIRs today do not have an IBR plant parameter verification requirement that is enforceable. And that leads to a lot of gaps, unfortunately, when a lot of engineering work has already been done in the design phase. I want to just touch on a topic that was mentioned by a bit by Jens, which is the distinction between model quality testing and design evaluation. Model quality testing might be part of it, but I see a very common misconception in the industry today that a model quality test like the ERCOT model quality test is a grid code compliance study for the plant. And that if you've passed MQT, you're basically done. And that means that you're going to meet all applicable requirements. I think it's well established that that's not the case. However, MQT is mandatory. No other studies are mandatory in some cases. So if one thing's mandatory and everything else is optional, the thing that's mandatory will be the thing that's done. And if MQT is the only modeling study that's been done for a project, ask yourself, what does that lead to in terms of plant performance? So the good news is that many of these things that I've talked about are really directly addressed in 2000.2. I think 2000.2 does an excellent job of putting together this comprehensive framework for conformity assessment throughout the project. But what it doesn't do is it doesn't say how a developer actually needs to execute that with all of their contractual sub-entities. And so that's really the work. And that's not a criticism of 2000.2. I mean, that's not something that an industry standard can do. That's something that we as developers have to figure out on our own. And the status quo situation, which I think is borne out by the latest NERC alert on IBR model quality deficiencies, is that we really aren't doing a good job of this today. And so if we want to now do conformity assessment relative to significantly more comprehensive and complex requirements, we're going to have to really improve our process around conformity assessment. So finally, just to say that 2000.2 is an opportunity to really improve all of this. However, I think that developers are really going to do it to the extent to which it is mandatory and that it is verified by some authority prior to building their plant. If this is something that is asked for but not verified, and it's a huge amount of work to do, it's very, very likely that it will not get done. So finally, this is the last slide. I wanted to end with just maybe one recommendation for different stakeholders in the project, and I'll start with my own. For developers, we need to have a much more proactive approach. The status quo situation that I've seen is that we're really doing things just exactly what you need to do to commission your plant. That is an approach that really adds a lot of risk to the project. And if we take a proactive approach during design to conformity assessment, I believe that really has a commercial benefit for developers in terms of the reliability of the plant after commercial operation. And we need to build capacity within our companies to actually do that. This is not something that you're going to be able to do 100% with consultants. For the AGIRs, I think enforcement really is the key. I've said that a few times. If you have a requirement, you need to know how you're going to enforce that requirement. If you create a lot of very complex requirements and you don't actually enforce them, what that means is that entities who do not comply with them will have a commercial advantage over entities that do comply with them, because they will not be spending the money to comply, and yet they will still be able to operate their plant. For OEMs, I think it's well established that unit OEM cannot on their own support the conformity or compliance of the entire plant. They can only enable, let's say, compatibility with conformity or compliance. However, I think OEMs can take a more active role than simply saying, here's our unit model, you do the rest. We've seen some OEMs now requiring customers to submit the IBR plant model back to them prior to commissioning so that they can verify that their unit has actually been modeled accurately. I think that's an important step, and OEMs have a bigger role to play, because ultimately, if the plant is not conformant or not compliant, that can be damaging to the OEM's reputation, even if it wasn't necessarily the OEM's fault. And finally, for the consultants, consultants are a huge and important piece of our industry. However, I think consultants need to be a little bit more careful about having difficult conversations with clients when clients ask for something that is not realistic or that does not make technical sense. If you're asked to deliver something with very, very limited information, the limitations or caveats of that work should be extensively documented. I understand that consultants are always constrained by the scope of work their client provides, but if the scope of work doesn't make sense, there is a role for consultants to push back on that a little bit. So that's all. Thanks for your time, and I'll be interested to hear what other perspectives and questions people have on that.
Thank you, Rishi. Very good presentation. Tremendous amount of very practical and pragmatic perspectives. So thank you for sharing that. We often don't hear those perspectives, and I think they're rather valuable in illustrating and highlighting some of the gaps that we face. So thank you very much for sharing that. I know that it takes a lot to share those humbling perspectives, and I know that they're very likely aligned with many other developers. It's not just one developer facing those challenges, it's many. So I particularly like all the moving puzzle pieces, and I liked your comment about if we drew the mapping, it would just be a giant spider web. So I'm not even going to try, right? Like that is humbling, but also very eye-opening. So anyways, thank you for sharing. Great perspectives, and we'll turn it over now to Patrick Hart to share the EPC side of the perspectives. So Patrick, I'll turn it over to you. We are running just slightly behind. So just keep that in mind. If you can keep it to about 20 minutes, that'd be great. Oh, you're on mute. Oh, try again. Maybe I can't hear you. Oh, no, can't hear you.
Is that better?
There we go.
Yeah, my apologies about that. All right, so I really appreciate Rishi's presentation before this. You're going to actually hear a lot of the same content because I think we're running into a lot of the same some issues. So I'm going to give real quick an overview of Mortenson and a quick introduction of myself. So Mortenson is an EPC that operates within the US markets. So we build a whole bunch of other things like stadiums, hospitals, and the like. But I've listed here the projects that are really within the energy space. My work is primarily focused around energy storage to help them kind of meet the challenging landscape of requirements and stuff that's happening there. On the energy storage side of things, we've been in this business for about 10 years, and we've been watching it begin to mature, right? While we've seen a lot of improvement, I think there's still a ways to go before I feel comfortable with the state of the industry kind of meeting what we're kind of setting out for it with IEEE 2800. I myself have been with Mortenson for about a year now, and I was brought on as a subject matter expert on power plant controls and kind of the design of the control narratives for our energy storage projects. Before Mortenson, I spent about 15 years developing PPCs for some of the largest and smallest players in the space. My favorite subject is hybrid power plants, and I can talk about that for hours on end. Mostly because there's a lot of really cool technical challenges and a massive amount of potential in the space. But here I think we're going to focus on the challenges that we've been observing from the energy storage side of things. Some of that does come with hybrids, but we'll focus on straight up energy storage projects generally. So kind of back to where Mortenson gets engaged. We have scope that varies from project to project, but generally Mortenson supports our customers from the IBR design phase through the commissioning of projects, often beyond COD. So because of the vast experience, like the painful learning experiences that we've we've endured. We generally get deeply engaged with the developers and owner operators to kind of help guide them towards some of the best possible outcomes. I know you guys hear a lot about the design evaluation window. So kind of this window of time right here. Well, my focus is kind of what's going to come afterward, right? Once a plant is designed on paper, our team is usually the ones that are there in the thick of it to make it work as requested. So that's not always easy, and the content I have for you today is going to focus on the projects we see from the problems that we see kind of on a project-to-project basis. So I also want to mention that a lot of what I cover doesn't always get considered during what we consider the design evaluation phase here, right? IEEE 2800 includes a lot that's not part of the power system studies. And that's kind of why I personally consider design evaluation to start when we're doing those power studies and then continue all the way up until pretty much COD, right? Because you're evaluating the compliance with that study or with that standard, and the things that you don't evaluate during the model studies is really kind of coming in when you're doing the commissioning of the project itself. So it's may be considered out of scope of that effort generally, but the impacts made by the decisions during the design evaluation phase have a big impact on being able to meet your schedules and getting the project up and running. So the hope is kind of that the understanding of what problems that we run into after this design has been finalized can help us as an industry kind of create designs that are better suited to meet those requirements in the first place. All right. So as we go through this, there are a couple of overarching themes that I want to share with you. First, for EPCs and honestly for everybody else for that matter, standard work is absolutely critical to maintaining the schedules, right? If you want to get a project to COD on time, you need to have standard work, right? If you miss the COD of a project, there's serious financial losses generally for everyone involved, right? So meeting schedule is possibly one of the most important things that an EPC will focus on. I've seen cases where we've settled on a suboptimal design because the alternative was going to create delays on getting to COD. So getting things right the first time is important, and that means you need to know what you need to do and how you're going to be able to do it. All right, so the next two, these are going to echo things that you've heard in the previous presentation, right? Product design is centered around test requirements. When there are standards, the things that are tested are going to be the things that get built into a product. If you don't test for it, it's probably not going to operate the way you expect it to. I'm going to sound repetitive, but the same goes for projects, right? The project design and commissioning is centered around test requirements, right? Stuff that's in the IA are going to meet requirements. If it's not in there, the facility is probably not going to be operating the way you expect it to. I want to kind of stress that this is not intentional. Engineers are really good at evaluating results against target behavior, right? So giving us targets, telling us what we're expected to do, how we're graded against those tests, kind of that's our love language, right? We respond really well to that. The last thing I want to mention is that OEM equipment is generally designed for everything under the sun, right? Across the entire planet. That means that there's thousands of settings for every single piece of equipment. And when an OEM comes to you and says, hey, we can do this, it's true. They probably can do it. But that doesn't mean that the commissioning teams that are going to implement it know how to set it up for any particular project. It also means that if you have variations from market to market, we're essentially asking those OEMs to provide more options on how to do what we're asking to do in these different markets, right? And if you're building that into a product, that means that you have more configuration settings. And this kind of brings us back to that first theme where if we have standard work, it makes it easier, right? So providing more options and more requirements and more variations on those requirements is going to bring us away from that kind of standard work theme. So I think our goal as an industry really should be trying to reduce the variation between markets to make standard work as easy as possible. All right, so I'm going to get now into a couple of the specific pain points, and I'll kind of move a little bit more quickly through these than I'd like to. But the first one is one of the most painful ones I've run into, and this, like, if I could clear up this issue, I probably would have gotten at least a third of my last year back. So a real quick recap. The IEEE reaction time is around 200 milliseconds, and reaction time is the amount of time it takes for a system to begin responding to a change in reference, right? So as soon as you see a step in control reference, you start the timer. Once you see a small change in output from the facility, that's your reaction time. And it often gets confused with response time, which is when you get up to a certain amount of response of that final output. That's not what I'm talking about here. It's really that just the beginning of movement. We set it at 200 milliseconds in IEEE 2800. I personally, at the time, wasn't really concerned about that because it seemed well within the capabilities. But at the time, I also worked at a provider, an OEM provider that did everything, right? So once you have all of that within your scope, it's a lot easier to say that you're going to hit those requirements. What we've seen is when you start pulling multiple components together from different OEM providers, being able to hit that 200 millisecond reaction time is incredibly difficult. So I have not yet seen a facility that has gone off without a hitch at the first time, right? There's a lot that goes into this, but the primary cause for missing those requirements are communication delays. So on the slide here, you can see a generic control diagram with the various components that are in there. And this essentially shows closed loop operation here, but the same is true as printing for open loop controls. If you just add up the communication delays that you see here, and these are pretty fast, it uses up about half of that 200 milliseconds on its own, right? So half of your time to get to that reaction time is gone. And that doesn't leave a lot of time for the rest of the components to do their jobs. During the remaining 100 milliseconds, your PPC has to generate the desired command, issue that to the PCS. The PCS needs to start changing the gating commands to its power conversion equipment. And then the meter has to be able to measure that and filter it and pass it back, right? Getting that all to work correctly, especially with 3 different OEMs for the different components is really, really difficult. So I think, and then that's actually like before you start putting in a hybrid plant control. So if you start adding a hybrid PPC on top of all that, for example, to like a control coordinate between a solar PPC and a storage PPC, that makes it pretty much next to impossible. One more item that I'd like to cover here, where you measure things is absolutely critical to measuring the reaction time correctly, right? If you are getting data from different sources, you're probably making things look better than they really are. Pulling the data, the control reference, for example, from the PPC, and then reading, say, the metering data directly from the meter itself means that you're bypassing that communication delay between the meter and the PPC. So what we've done in terms of best practices is really pulling all of the data directly from a single resource, right? And generally that has to be the PPC because the control reference is built into that as well. In order to make sure that we're kind of measuring things correctly. And when your reaction time is 200 milliseconds and your comms delays are on the order of the same time, it's really critical that those data points are kind of all aligned correctly. We had a case where the meter data looked like it was coming in the response was happening before the control reference was actually being changed. So making sure that everything is aligned correctly is absolutely critical when measuring this correctly. So what can we really do for this? I think ideally we get away from Modbus as the primary means of communication between pieces of hardware. That's going to be extremely difficult to do. Modbus has never, but like it really hasn't been designed as a real-time communication protocol. I think it was fast enough to support the needs of the industry in its infancy, but it was never really replaced as the controls requirements were going faster and faster. So another quick thing I want to mention is that the synchrophaser data that we've seen, we've actually seen that it's been buffered, right? So even that is not a suitable communication protocol out for metering purposes. So we've seen it buffered and all sent out in bursts of data sets. Yes, it's timestamped, but that doesn't really help the PPC if it's a kind of like 200 milliseconds late. So I think for design evaluation purposes, making sure that the models include communication delays that are realistic with respect to the equipment set being used and the method of comms that you're using, that's going to have a big impact on making sure that your model matches the actual performance that you're going to see in the field. I think that's the biggest one I want to hit. We'll go through the rest of them relatively quickly because I don't think we have all that much time. Data recording is not where it needs to be. This is not one of those things that you see during the model, the power system studies. So this is something that I think we've kind of missed as an industry. We found that a lot of OEMs are not storing data with respect to the requirements that we set out in IEEE 2800. We've seen movement and a desire to do that, but it's really not there yet. My suspicion is that the engineers that are designing IBR controls for performance, if you're looking at like LVRT and reaction time kind of stuff, are not the same ones that are doing the work that needs to improve the platform that the code is running on, right? So we need those engineers, the ones that are developing the platform stuff, the hardware that the code runs on, to change so that it can be able to do the recording that we need. On top of that, even if the OEM provides the capability to record that data, it's going to be extremely painful to pull it doing post-fault analysis, right? So yes, it might be compliant, but that means it's not pain-free, right? So you're going to have to bring an engineer out to every single one of these pieces of equipment and potentially pull the data from the equipment itself. So I think going back to Rishi's presentation, he had the Spider-Man mentality. Yeah, it's not my problem, right? Like it's a facility-wide standard. OEMs can point to somebody else and say, hey, we've provided you the data. It's your job to collect it all. So I think going forward, trying to find a way to make that process easier, providing the right interfaces and the right like standard approaches to extraction of data is going to be relatively critical to making this something that's not going to be painful to actually pull data from in the future. And I want to stress that like having been part of the team that develops code and products for a large part of my career, it's changing those kinds of things can be a lot of work. So sometimes the hardware has to change, and for an OEM that has a lot of equipment in the field, making those changes is not something that they're going to be able to do lightly. So that can take up to like years to implement if you actually have to change a platform that you're working with. So we're asking them to do a lot, and it's going to take time. What are we doing on time here? Speaking of time. All right, so I think time for synchronization, I'll cover this really quickly. We asked in IEEE 2800 for some pretty stringent time synchronization requirements. The 100 microsecond IBR unit level monitoring synchronization is actually extremely difficult to do without having a GPS clock for every single IBR unit, right? So if we're going to bring ourselves to that level of synchronization, it can be expensive, right? So if at the low end, a $3,000 like GPS clock for each unit is going to cost you like 200K per project, right? Then the question is whether or not that's required for us to get a good understanding of what the equipment's doing during a fault. If we can get away with what NERC has proposed instead, that's helpful, right? Because I can think of a lot of things that 200K can buy for a project. So just go to whether or not that's something we want to really push for. Back to the control settings that's left, right? I mentioned earlier that OEM equipment has thousands of control settings for IBR units. Often these settings are managed by the engineers from the OEM themselves, and the visibility to the developers and the owner operators is often limited. So beyond access to what the settings are, we found that on more than one occasion that even within a facility, these settings can vary from unit to unit. So I want to stress that only a couple of those settings actually have a material impact to the dynamic performance of a facility, especially when you're looking at the impact to validation of a grid model itself. But I want to stress that in general, those settings are not a one-to-one match to the equivalent parameters within the grid models, right? Others might have an impact, but only during specific conditions during which the facility operates. For example, when you're looking at energy storage facilities, at low SOCs, they may split up power commands at differently between the different units. That may actually have an impact on your performance at the facility-wide level in terms of how it pushes power to the grid, right? So those things are there. Depending on how detailed those models get, you may or may not be able to capture some of those behaviors. The last thing I want to mention here is that the field results are often pulled from systems that are running at ideal conditions, right? This might mean that all of the resources are online, with the prime power sources operating at stable conditions. My expectation is that when the grid is stressed to the point of failure, right? When we're looking to evaluate the performance against these models, those ideal conditions are likely not where our resources are going to be sitting. That said, like testing for all those corner conditions is going to be impossible. We can't do that. But I think it's important for us to understand what the differences might be present when the facility is kind of running on those boundary conditions, if that makes sense. All right, so I don't want to leave you guys all in despair. There is significant movement towards compliance across the industry. So I think a few issues here and there are expected. Most of these problems stem from either a lack of understanding of the requirements or a lack of understanding of who's going to comply with the requirements. So we see developers and owner operators often including IEEE as contract requirements, sometimes parts of it. Like Rishi mentioned earlier, if you can identify who's supposed to be doing what, that's far better. Sometimes we've seen a wholesale, this facility must comply with IEEE 2800. Honestly, to me, that doesn't mean much, right? Because it is extremely difficult for an EPC then to go turn around and say like this piece of equipment needs to be able to do this, or this one has to be doing that, right? Because it really is a facility-wide system, a requirement. We need a little bit more guidance than that, I think, in general. We're seeing a lot of OEMs working towards compliance at the unit level. The contribution of those OEM pieces of equipment towards site-wide compliance are a little bit behind the curve. But I think that's kind of expected. Just we need to hit the stuff that in order. And I think more and more we're seeing people become knowledgeable with the steps that are needed to achieve compliance, right? So I think most of that is as groups of vendors or developers go through and address problems that we've kind of described above, we get that kind of understanding of what we need to do to get it right in the first place. And I think the last thing I want to say is that even that we haven't actually finished IEEE 2000.2 yet, we're seeing some organization around kind of identifying the ways to test for it, right? I think one of the problems though is that we're seeing variations in these testing approaches. So I think, to be honest, like IEEE 2800 can't come quickly enough to help us kind of address that. Okay, so I think that wraps up the content I have. I think hopefully I did that within time. I'll hand that back to Ryan now. Thank you.
Awesome. Thank you, Patrick. Great perspectives, really informative and complementary to Rishi's presentation as well. So we can kind of open it up to Q&A now. Let me go ahead and share my screen.